Okay, so the next thing that we have about capacitors is just a very short discussion of basically what a capacitor is, how it's made, and then we will get to some calculations related to capacitors. Basically, what capacitors fundamentally do is that they store electric charges or electrical charge. So basically capacitors store electrical charge. Basically just like what a battery does, but of course batteries can do the same thing in a higher quantity, meaning it's not that the potential difference on the would be different. For example, if you connect a battery something like this, meaning that suppose you have this power supply here. You have this power supply here, and if you connect the voltage on this power supply, it gives you, for example, a voltmeter shows you that there is 10 volts potential difference on this power supply, and the two poles of this power supply. Now suppose that there is also a capacitor over here, and if you connect this capacitor to this battery, positive to positive and negative to negative, then of course what happens is that after 5 time constants, after 5 times tau, the voltage that your capacitor is going to charge all the way up to 100% of the power supply voltage. And now if you disconnect this from here, now the power supply reads 10 volts. If you measure the voltage using a voltmeter, the capacitor will read also 10 volts DC if you measure the voltage using a voltmeter. So basically, as far as the potential difference is concerned, they have the same potential difference. Now the difference over here is that now what happens is that if you connect, for example, this battery to a lamp, normally, for example, a typical battery could basically turn on a lamp for example 1, 2, 3, 4, 5 hours, even up to 5 hours with full brightness. There would be no problem. The lamp will just keep on glowing, and you would have no problem with no problems in the voltage. The voltage would not decrease, and you would not have any problems there, even up to 5 hours. Now the same lamp, now of course you need to take into consideration the fact that the potential difference on both the battery and the capacitor are both 10 volts. Now you connect the same lamp to the capacitor, and what you will see is that the lamp, after probably just a few seconds, it will start glowing, of course, in the beginning, but after probably a fraction of a second, or at most after a few seconds, or at most after a few minutes, it will start glow. It will stop glowing and then it will turn off. So what that means is that then the electrical charges on the plates of the capacitor have kind of run up. There is no difference anymore. There is there is no potential anymore. So when there is no potential difference, there will be no current, and so when there is no current, there will be no glowing of the lamp, basically. So what that means is that the potential difference that you can suppose that you basically charge this capacitor all the way up to 10 volts by connecting it to this power supply. Now the potential differences are going to be the same, meaning that the potential difference on the power supply is going to be 10 volts. The potential difference on the, by potential difference what I mean is exactly the voltage. The potential difference on the capacitor is going to be 10 volts as well. But in the case of the battery, connecting a lamp to the battery, this potential difference is going to last even up to 5 hours. It will turn on the lamp and the lamp will keep on glowing for probably 5 hours before the battery runs out. But in the case of the capacitor, then what happens is that the lamp will start glowing, but it will stop glowing after at most probably a few minutes. So the potential difference is the same. It's the same 10 volts, but the amount of the electric charges that the capacitor can store is much less than the amount of the electric charges that the battery can store, and so the capacitor will run out after a few minutes at most, but the battery will keep on going for hours and hours and hours. And of course that's not a problem with the capacitors. Capacitors basically do that because the capacitor is basically not meant to do the same thing as a battery does. A battery is supposed to supply you with a voltage for a preferably long amount of time. A capacitor is just a very smaller version of battery. It gives you a voltage or a potential difference for a short amount of time, and again you charge it, again you discharge it, again you charge it and discharge it, and that's basically what it does. So you can say that if you imagine that this battery is not a rechargeable battery, it's one of those batteries that you use only once and then you have to dispose it. So then, compared to that battery, basically this capacitor can be considered as a rechargeable battery, but with a very low capacity. So that's basically what it does. And basically what a capacitor is, it's basically two plates, or basically two you could call it two planes or two plates that can store charges. So one of them stores positive charges, one of them stores negative charges, and since one of them is positive, one of them is negative, hence the potential difference. And basically what happens is that you have your capacitor over here. Suppose that it is not charged. Suppose that it's not charged. You connect it to a battery. You connect your capacitor to a battery, and then this will be positive, this will be negative, and then you can disconnect you after the capacitor is charged up. You can disconnect this part, and now if you basically connect this to a lamp, for example, your lamp will start glowing for a few seconds, a few minutes at most, and then you have to recharge your capacitor. So that's basically what capacitor does. So now there are two types of capacitors. One of them is called the ceramic capacitor. It's called the ceramic capacitor. And the other type is called an electrolytic capacitor. Electrolytic capacitor. So a ceramic capacitor and an electrolytic capacitor, the difference between a ceramic capacitor and electrolytic capacitors is that, and of course I need to read over here. So it says that one of the most common types of capacitors is ceramic capacitor, which has values ranging from a few microfarads up to approximately 45 microfarads. The name for a ceramic capacitor comes from the use of a ceramic material to provide insulation between the metal plates. So it seems that there is basically two metallic plates, and of course you do need to have some sort of insulator material between the two ceramic plates. So this insulator is made of some ceramic material. So this part is your insulator, and these are the two plates of your capacitor, and this material is ceramic material, and hence the name ceramic capacitor. And usually these kinds of capacitors are usually they're small in size, and they go from a few microfarads or a few picofarads all the way up to probably 10, 20, 30, 40, which is very rare really, up to 10, 20, 30 microfarads tops basically. And and then another type of capacitor that we have is called the electrolytic capacitor. The electrolytic capacitor is different in that these kinds of capacitors are usually they usually last longer. They usually last a lot longer than electrolytic capacitor, and the reason for that is that the electrolytic capacitor, it has some material in it, which is called which is some sort of electrolytic fluid. So the electrolytic fluid is that fluid which is used in a battery. So in case you have read about batteries in chemistry in high school, you know that the battery is basically two metallic plates in a vessel, for example, in a plastic or glass vessel, and then there is these two plates, these two metallic plates made from different types of metals, and you have two different types of metal, and basically they are immersed in some sort of electrolytic fluid. This electrolytic fluid is basically is a conductor, and basically it is a conductor, and depending on the type of ions and all of the whole business going on inside the electrolytic and between the two plates in the electrolytic fluid, then the whole battery basically goes through the charging and discharging cycles of basically the charging and discharging cycles, and then you can basically then, for example, one of these plates would be, for example, positive and negative, and then you can, for example, connect it to a lamp or something, and then that will be a source of electric current. So it says that another common type of capacitor is an electrolytic capacitor available with capacitance values ranging from 0.1 microfarad to several thousands of microfarad. Now, I kind of got carried away. Now, the electrolytic capacitor is basically some metallic sheet and some electrolytic fluid inside the capacitor can. There is a can, and then inside the can there is this metallic sheet wound around in a circular shape, and then there is electrolytic fluid inside the capacitor as well. Now the insulator in this kind of capacitor is some sort of oxide on the surface of the metallic sheet. So then the electrolytic fluid inside the capacitor becomes, for example, your positive or negative, and then the metallic sheet on the other hand becomes the opposite of that. If the electrolytic fluid is positive, the metallic sheet becomes negative, and vice versa. And of course you do need the insulator between the two poles of the capacitor, and that basically that material that basically separates these from one another, that is that oxide, a very thin film of oxide on the surface of the metallic sheet. So that's basically how it works. So it says that another common type of capacitor is an electrolytic capacitor available with capacitance values ranging from 0.1 microfarad to several thousands of microfarad. The name electrolytic comes from the use of an electrolytic fluid, which, because it is conductive, acts as one of the plates, whereas the other plate is made of metal. The insulating material is an oxide on the surface of the metal. Now one difference between ceramic capacitors and electrolytic capacitors is that electrolytic capacitors, having the electrolytic fluid and all of that business inside, they are usually polarized capacitors. Most of the time. They have the positive pole and they have the negative pole, and you have to observe these two poles when you want to connect them to a circuit. Basically ceramic capacitors are most of the time non-polarized capacitors. There is no polarity there, and so you can connect them to the circuit in any way that you want. Although there is sometimes in some circuits there is some recommendation. For example, there is some specific types of capacitors that are not polarized, but it's recommended that you connect them to the circuit in such a way that, for example, one of the leads is strictly, for example, connected to the chassis ground of your circuit, meaning that, for example, to the negative side of your circuit, and the other, of course, the other pole then to the positive side of your circuit. And that, for example, reduces noise and that sort of thing in your circuit. But otherwise they're non-polarized. They don't have the positive and negative markings on the body of the capacitor. So it says that the name electrolytic comes from the use of an electrolytic fluid, which, because it is conductive, acts as one of the plates, whereas the other plate is made of metal. The insulating material is an oxide on the surface of the metal. Unlike ceramic capacitors, many electrolytic capacitors are polarized, which means that you must insert the lead marked with positive in the circuit closest to the positive voltage source. The symbol for capacitor indicates the direction in which you insert polarized capacitors in the circuit. The curved side of the capacitor symbol indicates the negative side of the capacitor, whereas the straight side of the symbol indicates the positive side of the capacitor. And then, of course, in a circuit, schematically, you draw them like this. So it would be something like this. This is a curved line segment. This is a straight line segment. And then if your capacitor is polarized, and you draw it like this, this becomes the positive, this becomes the negative, and then in the same manner it's connected to your circuit. And of course you know that the unit of capacitance is the Ferret. The unit of the capacitance is the Ferret, denoted by an uppercase F. Now, of course, the Ferret is just a name that has been given to the physical quantity. If you go into the physics of this, then of course Ferret basically refers to some, for example, to some physical quantity that can be expressed in terms of the base physical quantities, or the base units, meaning that, as you know, in physics we have basically the mass, the unit for time is second, the unit for example, the unit for mass is a kilogram, the unit for amount of substance is, for example, the mole, the unit for example, I don't know, electric current is amps, the unit for example, I don't know, luminous intensity is, for example, candela, and so on and so forth. There is 7 of these. There is 7 of these, 7 base units. And if you go into your physics, and if you get into the physics of these capacitors, of course the name, just for the sake of convenience, they have given this name, the Ferret, the name of the scientist, to the unit. Otherwise the unit would be expressed in terms of these base units, which would be something, of course, when you want to do more complicated calculations with your capacitor, you need to basically use the unit in terms of the 7 base units, which we are not doing really here in these videos. We will later get into the physics of basically we will get into physics in general, and then capacitors will also be a part of that. And so basically the unit of capacitance for now what we need for now is the Ferret, and all of your test equipment on your electronics bench are in terms of the Ferret, and but there is usually, for example, the microfarad, there is the picofarad, there is the nanofarad, and so on and so forth. And of course, you know what that means, meaning that for example, there is usually no millifarad. Millifarad is not very popular. There is a microfarad, which is 10 raised to the power negative 6 farads, and then nanofarad, which is 10 raised to the power negative 9 farads, or the picofarad, which is 10 raised to the power negative 12 farads. So, for example, if you have a capacitor with a capacity of, for example, 12 or, I don't know, 200 microfarad, that is the same thing as 200 into 10 raised to the power negative 6 farad. If you have, for example, 150 nanofarad, that's the same thing as 150 into 10 raised to the power negative 9 farad. Or if you have, for example, I don't know, 100 picofarad, that's the same thing as 150 into 10 raised to the power negative 12 farad, picofarad, right? Picofarad is negative 12 farad, for example, and so on and so forth. There is usually only capacitors are expressed in either microfarad, nanofarad, or picofarad. I can see I have a capacitor tester here, which it seems that millifarad is also there. Usually I've never heard millifarad, but if you have millifarad, for example, I don't know, for example, 230 millifarad would be 230 into 10 raised to the power negative 3 farad, for example. So these of course, these are extensively used in physics, and these are called prefixes and suffixes that are used in the SI unit, in the SI system. Micro refers to 10 raised to the power negative 6. Nano refers to 10 raised to the power negative 9. Pico refers to 10 raised to the power negative 12. And milli refers to 10 raised to the power negative 3. For example, when you say 2 millivolts, that's the same thing as 2 into 10 raised to the power negative 3 volts, which is equal to 2,000th of a volt. So that's basically how, if you know these four suffixes and prefixes, there is a better name for this. I've forgotten the name, but you get the idea. So if you know these four, you're usually good to go. And there is, of course, the other side of these suffixes and prefixes as well, meaning that these are the negative powers of 10. The positive powers of 10 are also there: mega, giga, and tera. So mega is basically when you say for mega is 10 raised to the power 6, which is 1 million, and the symbol for that is capital M. Giga is 10 raised to the power 9, which is the symbol for that is a G, that's 1 billion. And tera is 10 raised to the power 12, and the symbol for that is an uppercase T. Tera. over here. Tera is 10 raised to power, and that's basically I suppose 1 trillion, right? Because you have one, basically 1, 2, 3, and 4. So this is 1 million all the way up to here, 1 billion, 1 trillion. So that would be 1 trillion basically. And the symbols are uppercase M, G, and T. And on the other hand, then you have 10 raised to power negative 3, for example, which is called the milli, and the symbol for that is a lowercase m, not uppercase. Then you have 10 raised to power negative 6, then you have 10 raised to power negative 9, and 10 raised to power negative 12. You have 10 raised to power negative 12. So 10 raised to power negative 6 is micro, which is the symbol for that is the Greek letter mu. 10 raised to power negative 9 is called the nano. The symbol for that is lowercase n, and 10 raised to power negative 12 is called pico. No, not pico. I'm sorry. Is pico, right? Is pico. And the symbol for that is lowercase p. So if you know this much, you're good to go. You will have no problems in this course that we are doing here. And usually you don't even need these big ones, because usually what we do in electronics has nothing to do with these things over here. Now that's basically that. Now there is a couple of things about connecting capacitors in parallel and also in series that we will cover in the next video. So I'll see you in the next video.